Okay guys, so welcome to today's lesson. I am going to put the solutions to the homework up for you to have a look at. So I'm just going to make this slightly smaller so you can see it better. Okay, so pause this and mark your own work. And just to remind you, if there's an asterisk there, then that is the only acceptable answer. To explain how the marks work, if you were to get, say, 6 parts of this right, your first 2 parts are each worth 5, and the next 4 parts would be worth 4 each. So the marking would go like 5, 5, 4, 4, 4, 4, 1, 1, 1, 1. So if you get everything right, you get all of the marks. If you get 6 right, you only get this point, this point, this point, this point, this point, this point. And that's how they award the marks. Now, we haven't done the disorder of the eye or ear yet, so you should not be able to get marks for those at this point. The one that we are going to do when we do it is a thing called glue ear, and the corrective measure is either eardrops or grommets in surgery. So we'll talk about those at a later date. Okay, so pause now, and this is for the 2009. And again, you should be able to access everything, and you can just see here the marks are very straightforward in how they're allotted. So for part 3 here, you need 3 answers, and each answer is worth 3 marks. So pause and mark for yourself. So today we are going to talk about the functions of the ear. It is roughly page 164 in my version of the notes book, and again, it is a big, very giant table. So we're going to start with the pinna, and the information is already there. So the pinna is what we would call your ear, and its job is to collect and channel the vibrations into your auditory canal. And we've said that all of the kind of wrinkly bits that are around your ear, their function is actually to focus the sound into your ear. It is made of cartilage, so it's not made of bone, so it's much more flexible than bone would be. Your auditory canal then will carry the sound vibrations down your ear or down this canal. So the sound vibrates essentially air molecules, and that's carried down into your auditory canal. And you will have wax secreted outside your eardrum, and that has a protective function. Obviously, too much earwax and your eardrum can't vibrate, so that's not so good, but it is in there to protect dust and other particles by picking them up. So then we have your eardrum, and in your eardrum it vibrates when air vibrations reach it. So me talking now, coming out through your speakers, is vibrating the air molecules. It's going down your auditory canal, and then it'll start your eardrum vibrating, and it's a really small stretched membrane, literally like the skin of your drum, and it separates your outer and your middle ear. So really the most important part of this is the idea that it vibrates when air vibrations hit it. So then we get into our middle ear, and these guys are called the isosceles altogether, so the hammer, the anvil, and the stirrup. They are the smallest bones in your body, and they transmit the vibrations from your outer ear into your inner ear. And what they also do is, as each of these little bones up here vibrates, they increase the level of the vibration that's going to be picked up by your cochlear for hearing. So that is these guys. So they're the hammer, anvil, and stirrup, we've said already. So as well as having your isosceles in your middle ear, you have your eustachian tube. So if you've ever watched Bill and Ted, I think it's Bogus Journey as opposed to Excellent Adventure, there's eustachian, I'm fairly certain, quality movie. So your eustachian tube is, again, a protective mechanism. It prevents damage caused by pressure differences between your outer and your middle ear. So again, we go back to, if you hold your nose now and breathe out, your eardrums will pop out, and if you yawn, you'll feel them click again. And when you yawn, you're using your eustachian tube to equalize the air pressure. So really important when you fly, really important if you go diving, because you don't want your eardrum to burst. Technically it isn't part of your ear, but it goes from your ear down to the back of your throat. Okay, so after this now we're in our inner ear and we have our cochlea. So this is the snail-like part, and this is responsible for your ability to hear. And what it does, and I'll show you some video that will help. So we have gotten to this point and we have vibrated the isosceles, and what happens is that we've said that this inner ear is filled with liquid, and that liquid, now think of it like a wave being passed along, coming from outside into the shore, but that wave will travel through your cochlea and it converts that pressure wave into an electrical impulse, which is going to go to your brain. Okay, so obviously you have your, going to show you some video now that will hopefully clarify some of those things for you.
Have you ever wondered how sounds make their way from the source all the way to your brain? Take a trumpet, for instance. When it's played, it makes sound waves in the air. The outer ear catches the waves, which then travel through a narrow passageway called the ear canal. The sound waves reach the eardrum, which is a membrane roughly half the size of a dime. They make the eardrum vibrate, which in turn vibrates 3 tiny bones called the malleus, incus, and stapes. These bones amplify or increase the sound vibrations and send them to the cochlea. The cochlea is shaped like a snail and is the size of a garden pea. It is filled with fluid, and the sound vibrations make this fluid ripple, which creates waves. Hair-like structures called stereocilia sit on top of hair cells and are grouped together as hair cell bundles inside the cochlea. The hair cells inside the cochlea ride these waves, and the hair bundles are moved. The hair bundle on top of the hair cell turns these movements into electrical signals. As the hair bundles are moved, ions rush into the top of the hair cells, causing the release of chemicals at the bottom of the hair cells. The chemicals bind to the auditory nerve cells and create an electrical signal, which travels along the auditory nerve to the brain. Different hair cells respond to different frequencies of sound. The hair cells at the base of the cochlea detect higher-pitched sounds, such as a piccolo or flute. The hair cells toward the top of the spiral detect progressively lower-pitched sounds, such as a trumpet or trombone. At the very top or apex of the spiral, the hair cells detect the lowest-pitched sounds, such as a tuba. The auditory nerve carries the electrical signal to the brain, which interprets the messages as sounds that we recognize and understand.
Okay, so we've done that one. So that gives you an idea. So when he's talking about those pressure waves and those hairs, because you're younger than me, you have more of those hairs standing upright, so you can hear a huge frequency of sound, whereas for me, I can't hear very high pitches now anymore. They're less and less. So I don't know what it's like in Kilkenny, but I know in Cork there's an area in town where there's a shopping centre and loads of young people love to hang out, and supposedly they play a high-pitched sound which should annoy said young people, and leaving me, the mature shopper, to wander around the store and outside. But that, I don't know whether that's true or false, because there's always kids outside it, but there you go. So this is a little kid that's after getting her little cochlear implant, or she has a hearing aid that's going to help her. But similarly, when you get...
Yeah. Hello. Hello. I've never seen that face before. Hi. Are you emotional? You're gonna make me cry. Hi.
So bless her, it's all too much. So little kids, if they get cochlear implants, they will get a little device put literally into their skull through here, and that helps them with their vibrations and being able to interpret the sound. This one is also quite cool.
Silent, you can hear your heart beating and your lungs filling with air. It might sound like science fiction, but it's actually a place here on Earth recognized by the folks at Guinness as the quietest place on Earth. NBC's Gary Sanders took a trip inside.
In the chaos of our world, where there is seemingly no escape from noise, Petty Officer Third Class Nick Hare wanted complete silence. For the last 9 months, he's bunked just feet below the deck of the USS Abraham Lincoln.
You know, it's loud and noisy. It's like living under a roller coaster.
At Orfield Labs in Minneapolis, in a chamber the Guinness Book of World Records says is the quietest place on Earth, where you can literally hear a pin drop, this sailor asked for an escape.
Okay, let's settle in. It's the world's quietest room. Cool.
I endured the chamber for just 5 minutes.
There's like this intense pressure, sort of like you're in a car driving up a mountain and you keep having to swallow and yawn to equalize the pressure. And I'm pretty sure what I hear is the blood flowing in my neck.
The ear is both a loudspeaker and a microphone, and when it's deprived of sound, it produces its own. It creates its own aural hallucinations.
Why does this chamber exist? To test product sound levels, like hospital equipment, vacuum cleaners, or just this once for a sailor on overload.
It is becoming a little disorienting. It's interesting.
I'll bet after 10 minutes, Nick might think he has now had that experience and he's ready to move on.
Nick Hare lasted more than an hour.
How are you?
I'm okay.
Let's see if you can actually stand up.
Okay.
And how do you feel?
I feel wobbly.
A sailor getting his sea legs.
Do you hear those planes landing?
Not
on
right
the
now.
aircraft carrier?
I can't do it right now. It's really interesting.
So it is erased.
I believe so.
And finally, that elusive peace and quiet. Kerry Sanders, NBC News, Minneapolis.
Alrighty, so I think they're quite cool, those three things. So now just in terms of how our cochlea works, if you have to describe it, so again it's that snail part. The vibrations from the stirrup will arrive at your cochlea. They'll form pressure waves in the lymph, and the waves stimulate receptors, which are the tiny hairs, and these are attached to sensory cells, and these receptors will cause an electrical impulse to be sent to your brain along your cochlear nerve. So if you can think of it in terms of a process and see it in stages, then you will be fine. Now this won't work, but we saw it in the earlier video in terms of these are supposed to be the air vibrations going into your ear. This won't quite work, but in terms of how the air hears, so air vibrations are collected again by your outer ear. They're passed to your middle ear, where the vibrations are amplified. They're then transferred to the fluid in the cochlea, and again the receptors will cause electrical impulses to be sent to your brain. So please note that in the last two sets that we've been writing, one is how the ear hears and one is how the cochlea works. So two different questions, so be aware of that. So the last bit that we're going to do today is just going to look at our semicircular canals and how do they work.
The organs of balance, which influence the action of the cerebellum, are located in the inner ear adjacent to the organs of hearing. The position of the three semicircular canals and the saccule, the utricle, and the endolymphatic duct are shown in relation to other structures in the inner ear. A cross-section of the semicircular canals, which consists of three tubes, are positioned at right angles to each other in different planes. They are filled with a fluid known as endolymph. In the base of each semicircular canal are hair-like receptors. Any movement of the head causes the fluid within the canals to move and so stimulate the receptors to send information to the brain about the direction of the particular movement that has occurred. The utricle and saccule contain receptor cells with tiny stones of calcium carbonate otoliths. The otoliths are relatively mobile and movement of the head causes them to move. This changes the pressure that they exert on the receptors, which then send information about the direction of the head's movement to the brain, and illustrate the three planes of movement in which the head and body can move to stimulate the receptors in the semicircular canals.
Now I'm just going to put him back to here.
Send information about...
And I can't now draw on this particular screen, but if you are capable of finding a wall or a barrier that you can stick your head over and put your head in an upside down position, so it'll be like being on a trapeze, you will actually be able to kind of hear the stones moving. So there's these little calcium stones in your ear, and when they move, they cause a wave of pressure, and the little brown and the green and the little blue receptors pick up that pressure. And each of those three semicircular canals will know whether your head is moving, backwards and forwards, up and down, or left to right. So it's able to figure out in three-dimensional space where the hell your head is and give your brain that message. So take some time, do a handstand, and see can you listen and you can actually hear the little stones move. It's kind of freaky, but it is also kind of cool. Alrighty, so in terms of our last little bits of this, so we've said our semicircular canals are these funky looking things, and they are responsible for balance. So when you were learning to walk, your semicircular canals were giving your brain information about to where you are. Now you can balance without thinking, which is great, but when you're learning to walk you can't. Again, they're filled with the liquid, and they have different receptors to detect the position and movement of your head. They will send their message then to the brain via the vestibular nerve, it's called. And we will do cerebellum when we do the nervous system and the brain. In terms of then, you have to have a disorder of vision or a disorder of hearing. I picked the hearing one because a lot of people have had this condition, whereas there's lots of people with perfect eyesight. So we're going to look at what's called glue ear. And this is essentially when the sticky fluid that's released to protect your ear, but it actually stops your eardrum from vibrating. You can notice it in little kids. So I had a nephew that all the time said, I would like, mummy is drinking toffee and are you chumming? Because that's what he was hearing the sounds as, because his eardrum wasn't vibrating. So the kids that have glue ear, they can sometimes speak funny. So it is literally a build-up of sticky fluid behind the ear, and then your isosceles can't move and your eardrum doesn't really vibrate, and it can cause some degree of deafness, but it can also end up with speech difficulties because you're not hearing the correct thing. So there are a couple of things they do. They can give you nose drops. So they stick the drops up your nose, it'll go down the back of your throat and it'll hit your eustachian tube. In very severe cases, they'll insert grommets into your eardrum. So I don't know if you've ever been swimming in the pool and you see little kids wearing like headbands, and the reason they have that is because this grommet is a little circle, but it actually has a hole all the way through, and the gunk will come out that hole. So if they were to go swimming and water was to get in there, it would have water in your middle ear, and it'll go down the back of your throat obviously, but you will be deaf for a while because of it until you get rid of it. So the grommet allows air into the middle ear, it allows the sticky fluid to move down, and once the child grows, the grommets will fall out, which is good. You can only, again, I like use pieces of information, but essentially you can only ever if you burst your eardrum a second time, you will have some type of hearing disorder, so you can afford to do it once, but not really twice. It's not recommended. So use your eustachian tube and repressurize by yawning or blowing out through your blocked nose. So that brings us to that.